afternoon talk, which is also the official seminar of the GCS. The others were unofficial, but we will have seminars on Wednesday. We will try to have seminars on Wednesday from now on. We have the pleasure of having Onno Bokhove giving a talk today. He is a participant of the other program, but he has agreed to speak about his geometric integration and compatible discretization methods for us today. Thank you very much. The title is A New Wave to Wire and Wave Energy Model from VP
Variational Principle
to compatible space-time discretization.
Well, thank you for letting me speak. I'm going to talk about something very practical on the one hand, but on the other hand I use methodologies. Well, the methodologies are very relevant in this case. So I'm part of the other program, so this picture refers to the other program. It's a diagnostic on flood mitigation. I'm not going to talk about that, I can tell you. And this is actually a sketch of the wave energy device. So it's worked together with Anna Kalogiru, who's now just started his lecture in Nottingham, former postdoc, and with the artist and designer Wout Zweers, who is in the Netherlands. He'll come back in a later slide with some of the things he made. So I'm going to talk about this wave energy device. It will become clear. It returns several places. So basically a wave is coming in, so this is the surface of a wave, water wave, in a contraction, so it's narrowing, it's confining, and then in the contraction we have a buoy here, that's the red bit, which can go either up and down or move up and down under a slight arc. And then on the buoy there is a mast or an arc. There are coil magnets here, and the magnets go through a series of coils. And the coils, this is the green and the red, they are the loads. The coils are connected to the loads, and they're indicated here in green and red. And those are LEDs, which is just because it was a simple description as a load. And the LED only works when the current goes one way, and therefore they're in parallel, so that when the current goes the other way, because the motion goes up and down, so it changes directions, there is always energy generated, and energy here is generated in terms of light. And I'm going to I'm going to tell you that you can describe this device with a 1 ground variational principle. Since it's very hot, in any case, interrupt me whenever you want to clarify. I shouldn't point to the laser, put the laser pointer to you. Interrupt me at any point when you need a clarification. So, just some references. The top two about the wave energy device. We're going actually to a wave engineering conference, so that's pretty exciting. And I did some work, that's why I offered, on time integrators, or combined space and time integrators in water wave problems, which are all compatible. They discretize the variational principle in space and time, sometimes even in 4 dimensions. What you end up with is algebraic variational principle. You take the variations, and then your equations, your discrete equations of motions, the ones which you implement on the computer, they fall out. So that falls within the remit, I suppose, of the program. So I'm going to tell you what the variational principle is. There are some subtleties, because I allow weak incompressibility. I allow incompressibility in the weak sense. The waterline motion is actually the critical issue, and we use Lagrange multipliers to deal with the buoy and the incompressibility. Then I will very quickly simplify and even further simplify to make it palatable to you, because otherwise there's a massive amount of equations. And I will highlight the constrained character of the formulation. And then we use a trick which is unfortunately suboptimal in terms of the convergence you expect, but it converges. And I show some preliminary outcomes of simulations. Let's start how it came about. you may know or may not know what rogue waves are. Well, rogue waves are anonymously high waves which you can find at sea, but actually you can even find them in your cup of tea, according to the definition, but usually you're not getting excited then, unless you know about them. Well, so a definition in terms of the abnormality index, it's not artificial intelligence, I didn't make up the AI, it's abnormality index, it is the wave height of the rogue wave over the ambient wave height HS, which is a kind of poor man's definition, and this needs to be bigger than 2. There are some more profound definitions in these review articles, but that's roughly the definition. Then if it's bigger than 2, then I suppose it's because of linearity, then it's non then you have a rogue wave. It's relevant in maritime and coastal engineering. Usually people show ships which have been damaged, pieces taken off by these rogue waves, or even sunken ships, so I'm not doing that. Instead, I show you a pyramidal rogue wave. So this is a wave due to crossing seas in the sea south of Japan, and people always ask, this is about 10 to 15 meters high, because you can't see from the scale. But in some sense it doesn't matter. It's this definition which matters. If your ambient wave height is 15 meters, then your rogue wave height needs to be bigger than 30 meters. So it's a relative scale. That's why I say you can even get them in your cup of tea. I made them in the lab actually, but then they were small, but then the rogue wave was, right? It's all relative. But then people usually don't get excited. There are lots of explanations. Spatial wave focusing, well, the ones which interest me or are relevant here are spatial wave focusing. It can also be due to coastal convergences, so they can also be near the coast. Some tsunamis can even be a rogue wave. Episodic waves generated elsewhere, crossing seas. And then I made one by accident. And you can argue whether this is really one or not, so let's see if this works. Oh. Why are you doing that? It's supposed to be off. Good. That's it. So the wave is made by the sluice gate, and in the contraction, boom.
Whoa! Is this a science festival?
No, it was done in 2010 when I was at another university, the opening of a square, and they asked me to make a wave feature. So the story is I knew how a peregrine was doing, but I added the convergence, and then I tuned the wave height. This is not relevant. This is for the...
Want to see the wave again?
Yes, so there is a sluice gate, an excavator guy, right? We needed to do it with makeshift things. There is a sluice gate where the sluice gate is a lift out, not infinitely fast. It needs to be finite, and there's a difference in water level. So then, actually, a compound of solitary waves, a big one, and then a slightly smaller one, and then a very small one, comes in. As it turns out, it breaks, but you will see that right at the end here, it unbreaks, so it's smooth again. It has dissipated its energy. And the first one reflects and is not too exciting, but then bang, the second one crashes exactly in the trough. And it's that tuning which matters. If you change the water levels to 2 centimeters, the effect is gone. So this was, and I didn't know anything about rogue waves at that time, and then people said, you have done something profound. Oh well, all right. It has to do with rogue waves. Now, of course, in the sea you usually don't have that convergence, but you can see those walls as virtual walls with seas coming under an angle, so that effectively there is no flow there. And of course, then it doesn't reflect, then it goes through, and at one point in space-time you have the splash. And that's actually what I pointed out to Yuji Kodama with Kadomtsev-Petfiashvili equations. You can find exact solutions of this, but then without the reflection. And he could get to, I pointed out what he should do, because I didn't know about the theory, but I had a hunch because of the geometry in his pictures. And he got to, it's not 9 actually, 3 solitons of amplitude A get an amplitude of 8.6 A. I mean 3 squared would have been nicer, but we couldn't get the squared. It's 8.6 A. When you do this with 2 under the right angle, you get 4 A. So 3 makes this. And so this has a relationship with, of course. now, how does that? Okay. So then, if you saw that splash, if you freeze it and make silhouettes, well then the artist wowed spheres made of the silhouettes two pieces of, well, two sculptures, and you will notice they're outside here. So at some point we donated them to the Newton Institute. So they're not abstract art. They're actually the splash while it's collapsing. So that would be, so fits in the mathematical. And there's a story online how we came about making them. So what that led to, well, now you see how the wave energy device came up. We figured that in a contraction you amplify the wave. Now of course there's not going to be one wave at C, but just a series of waves coming in, but you amplify, so it's the logical thing to put a buoy there. Constraint, the buoy is related, has magnets on top of it, and that via the magnets going through coils you generate the energy. So in this case, in some cases I do it the other way around, but in this case I didn't want to make up a difficult mathematical theory and then find out that it was a whole hopeless and the wave energy device doesn't work. So again, with this artist, we made in 2013, it was also 35 degrees, you'll see a bottle of non-alcoholic beer. We made a makeshift tank to see if anything worked, just to avoid that it was all nonsense. So it was hand-held wave maker, so I was the wave maker. Because with this guy, usually everything worked, but the first thing is scrap heap. So this is the bottle of beer, non-alcoholic. You can't see that, but it's true. This is the convergence. This is the buoy, which has here a flat surface, but then we made it into a simplex to avoid splashing, so that it heaves up better. Here we put the coils in, and in a second you'll see what we did, how the idea came about. It's actually a deconstructed, it's coming in a second, come on. It's a deconstructed Faraday shaking lamp, and it's coming in a second. Yeah, this way, it's deconstructed, so we put the coils around the tube, and then there is one magnet in here, so we used two of them. We had 4 coils and 2 magnets on top of a mast, which goes up and down, and in a second you will see there is a LED, and you see the movie. So it's a makeshift motor. Then we made an Arduino scope, which is that cheap if you're smart. Well, my mate was smart, right, so he knew how to do that, because Arduino, an oscilloscope is very expensive, but with Arduino technology you can do that, which I didn't know anything about, but now I know a little bit. And that's the power. I want to wait till the movie comes. Oops, I don't know why. Anyway, we leave the sound, but here you see the splashing of the light, but since there was only one LED in one direction, it doesn't work when the motion goes down, and now we put things in parallel so that it works in both phases. So now I hope everyone who is not clear about what this device does, right? Is everybody clear? Good, because then we're on board. I'll thrash out the variational principle of the whole thing in one go in a second. Okay, so this is because this is important. In that sense, it's applied. That's it. That's the device. And I'm going to use 3 principles, not yet variational principles. So the first thing is that when damping and wave breaking are absent, the appropriate models, coupled models in this case, should be conservative, right? So if I don't have the electric resistance, I ignore viscosity because the waves are fairly fast, then it has a conservative limit. The second principle is that I write down the model for this wave energy device simply as the sum of 3 variational principles, namely of each separate system. And then usual, you need to have some experience, I suppose, by taking the integration by parts, you see whether there are missing terms, and in this case there are not even missing terms. You get the whole thing. And the coupling is in the integration by parts. The third principle is, so I have simply between quotes, right? I mean, what's simple? You can argue about that. The third one is that when you discretize this space-time variational principle, that with compatible integration you get a discrete algebraic variational if you use finite-element system, when you take the variations, then semi-automatically you get your whole discretization. So it's simple. But I mean, kind of, if you can't follow the details, that's what we did. So just a sketch of the tank cross-section, right? So if there is no x direction which comes out of the board, but just the vertical direction, the y direction, the free surface, then this simplex is simply a triangle, right? But it fits in a contraction. So if you look, when you look at it from above, no, one second. So what's important here is that there is a waterline point, because when there is a lateral direction, there is a waterline, which is not at one point, but it waves about. And it waves about because the buoy is in the contraction, so there is here a waterline where the water touches the buoy, and that can in principle be 2D horizontal. And there's a wave maker here, and this is a particular size for another tank we used. This is the top view. So, and the object, the buoy, is going to be simplex. Now, this is it. Now you're getting confused, and I'm after this simplifying it, but this is the whole thing. Oops, what did it do? This is the entire variational principle. So it's a functional in space and integrated from the beginning time to the end time of a whole load of variables. Now all these variables come in pairs. They're conjugate pairs. These two, these two, these two, and these two. And then these, the pressure and the pressure under the buoy, are Lagrange multipliers. Now this is a field. This is the pseudo density or scale density. This is the velocity potential, and they're function of x, y, z, and t. Now these are fields which are only functions of the horizontal coordinates of x, y, and t. This is the position of the buoy and the velocity, so it's just a function of time. This is the charge, and if you take the time derivative of the charge q, you get the current. And this is the conjugate of q, and in the coupling it is not the current. It turns out it's a slightly different variable. And this is again a three-dimensional Lagrange multiplier, function of x, y, z, and t, and this is a two-dimensional Lagrange multiplier, so it's a field. So these are fields and these are fields. So now the structure is like this. You have time derivative here a partial derivative. Since this is only depending on time, the dot is just a straight derivative, and then you have here the Hamiltonian, and with this definition, the Hamiltonian is defined as all the other terms which don't have the time derivative. And I sneaked in, maybe it's a bit sneaky, the constraints as well. So this is complicated, and last week when I did it, people got lost here. Well, that's all right, but this is just the beast. It's a beast, but the separate parts are easy. So now you must be used to a more mundane variational principle, which is just p dq dt, or let me just use q dot. It's a poor choice, so let me make the p with, it's not that p, it's another p, so I put these things there, minus the Hamiltonian, which is a function of p of q, and if you wish, when it's non-autonomous, it's a function of time. Right? I'm sure you're happy with that. Well, this is no different. The D is a field which kind of is the P in the water. The phi is a field which is kind of like the Q, but in the field form. In effect, the velocity in 3D is the grad of phi. So phi is a velocity potential. And when we look further, I have minus mw set dots. So mw is p, and for some odd reason, I loved it better like this. And the reason is that in waterways, they always write this and not phi d minus phi dt dd dt. So I flipped everything around. So then here, the W is like, the MW is like the P, the Q is the position, and then you see here half MW squared is the kinetic energy of the buoy motion, and mgz is simply the potential energy of the buoy. And this is the kinetic energy of the circuit, and this is the kinetic energy of the water, so it's in the field under the integral, and this is the potential energy of the water. And then this glues, this is an important term, this glues the water and the buoy together. So let me make a sketch. It's even in the next page. I say that the next page. So this is the difficult part. Next page, I make a sketch. So let's just do this h variable is a function of x, y, and t, and it's actually the water depth. Now, where the buoy is not, it's free, and the water surface can freely move. However, where it's under the buoy, the shape of the buoy, which can go, and the buoy can go up and down, the shape of this line stays put. So here h should equal, so this is the vertical direction, the buoy shape is defined as hb of x, y, and the time dependence is exclusively in this function, the position set of t, which is basically some reference position, or if you wish, the center of mass, but you don't quite need the center of mass. So in other words, here the depth must equal the shape of the buoy, because otherwise there is something wrong. And we say there is only one waterline point, or only one waterline. So how is that imposed? How is that imposed? That is imposed here by saying this Lagrange multiplier times the constraint that h minus hb should be 0, so h is hb, and this only holds for y bigger than yb. And yb is this waterline. So here is this Lagrange multiplier lambda defined. Now another one you see here, another constraint you see here, this is the Lagrange multiplier, the pressure, which is multiplied times d minus 1. So in other words, this pseudo density is 1. That says that the water is incompressible. But rather than substituting that in the variational principle, which I can do, we didn't do that. And the reason not to do that, I'm not getting to it, but the reason not to do it is that if you don't do that, then the boundary condition on lambda falls out of the variational principle. But when you put in d as 1 everywhere, then you have to a priori say what the boundary condition is on lambda at the waterline. And so if you didn't know that, and at some point I didn't know, or well, I had a hunch, but I didn't know it mathematically, and this way you can derive it mathematically. Now I'm not even going to take the variations and derive the equation of motion for you. I actually did one. If you take one variation delta p, then you get d minus 1 is 0, because taking the variation is for this simple term just taking the derivative. And same here, if you take delta lambda, so I'm going to derive you two equations. Delta lambda gives you h minus hb is 0 for under the buoy, so for y bigger than yb. And the rest is more elaborate, but you get all the equations for all these unknowns out of this, just, well, something, by magic, right? It's kind of Renaissance thinking. So I'm not going to show those to you, because it's a load. So I'll leave this as well, most of it I said. What's hidden under here is that we derived the electromagnetic motor via Maxwell's equations, but Maxwell's equations are reduced for an axisymmetric case and for very thin wires. But we started from first principles. First principles, and it's actually 8 pages of the 40-page paper. I mean, it's a bit hard because I couldn't remember any electromagnetic theory, but it's in that sense consistent. And it basically, you end up with one big geometric factor, some function of the position of the buoy, and there are triple integrals all hidden in there, which solve basically the Maxwell's equations. Now, what I'm going to do is I'm going to linearize. If you linearize the equations you get out of it, you get equations which are linear in the variables. And it's still too complicated, so I'm not going to say anything, except here. When you vary the variational principle, you get that this variable dp q dt is 0. And now what I've done here, I've added all the resistive terms and the loads from the LED lights, and they basically give you that there's linear damping on this aspect. So I said it as one of my principles. I derived the variational principle for the case when there is no damping, and then a posteriori, because it's easy to do, I add the damping, and then you get these extra terms. So these do not follow from the variational principle. All the other equations follow from the variational principle. Still too complicated, so now I'm going to make a few simplifications. I'm getting rid of the generator. Now in real life I don't do that, I just do that for this talk. I take a triangular buoy because I'm going to be in a 1D domain, so it's just this triangular wedge, and the x direction I take out. This is the domain. So you have a domain from 0 to yb, which in the linearization is a constant which I call lb, and the domain goes to ly, where there is a wall, and this buoy can go up and down. So I have two domains, d1 and d2, so d1 goes from 0 to yb or lb, and d2 goes from lb or yb to ly. So this was a nonlinear position, but when you linearize it's fixed and it's called lb. And then the equations of motion are actually a lot simpler, and I now hope you are on board with the equations. So we now only have wave, these are the wave equations, a buoy, which are the blue equations, and then a constraint equation. So instead of h minus hb, where hb depends on the big capital set, when you linearize, you just have to believe me, you get that eta minus set tilde, this is the perturbation from set, is 0. Now eta is defined as follows. You have a reference level h naught, and then this is the small amplitude deviation eta. So that's why it's linear. And this capital set here is defined as a reference set level when the buoy is at rest, plus a small amplitude perturbation, and that's the tilde in there. Now, look at these equations. If you take lambda tilde is 0, then these are the wave equations. So if I take lambda tilde is 0, then you recognize these are the wave equations. So d eta dt plus dy h of y. This is a reference background depth. dy phi tilde is 0, and dt phi tilde plus eta is 0 because when I don't have any y tilde. So if I now take the time derivative of this equation, I get dtt phi tilde plus the eta dt, but then I can substitute here, so I get here t dy, h of y, dy phi tilde is 0. So this is the well-known wave equation, right? And then what do I have here? Here I have the motion of the buoy, so the position of the buoy, the time derivative gives you the velocity, and this is using Newton's law. The motion, the velocity of the buoy in the vertical equals the pressure, the force from the water. It's the force from the water, so it's integrated from here to here. So it's integrated from 0 to ly, but this is a theta function, so it's integrated from lb to ly, right there where the buoy is wet. And then c is some constant, we find it here, and eta is really g eta, but I kind of scaled it a bit. Now, this is where a trick comes in. Methods need to be consistent. So I have this constraint, but the constraint needs to be preserved in time. So if I take the time derivative of this, then I get the eta dt. I can use this equation, substitute this in here. I can take dz dot, I can substitute it by w, and I get a secondary constraint. Now the secondary constraint also needs to be preserved in time. So I have the primary constraint, eta minus set tilde. I take the time derivative, and when I take the time derivative, I substitute this, so let me do that because it is important. So the eta dt is minus dy h of y dy phi tilde, and set dot tilde is w, tilde. So that means that the eta t minus z dot tilde, that's 0. That should then be minus this here, dy, h of y dy phi tilde minus w. And that gives me the secondary constraint, which I've written here, and I've taken off the minus sign. Now I need to take care that this needs to be true in time. So the consequence of taking the time derivative is that this needs to be 0, but this also needs to be 0 in time. So what you now need to do is take the time derivative of the secondary constraint. So I'll do that. And again use the equations. So what do I need to do? I need to take the time derivative of this one. So that's y dt, what do I get? Phi tilde plus the time derivative of this, and this needs to be 0. Now this, of course, I have an equation for this term, and I have an equation for this term, which were on the previous slide. So I substitute those. So I substitute the right-hand side of this equation in here, and I substitute the right-hand side of this equation, so this term at the other side, and when I do that, I get the elliptic integral equation for lambda, because lambda appears here and lambda appears here. So if you take this operator working on this term, you get this term, and this term emerges here. So this is an elliptic equation with an integral, and on the right-hand side you have a source term. But now there is something odd. We have 1, 2, 3, 4, 5 unknowns, but we have 1, 2, 3, 4, 5, 6 equations. There's too much. So now we have the choice. We can either solve the first 5, or we can solve the last 5, but because they're equivalent, I just showed you, I just made clear they're equivalent. So this means that in a discretization, you want to preserve that property. You want a discretization such that the discretization of your discrete constraint, the time derivative of, gives you a secondary discrete constraint. The time derivative thereof gives you a discrete integral elliptic equation, which a priori discretization needs to be all matching, otherwise you're in trouble, otherwise it's not consistent. So that's then the goal. And I also wrote down the boundary conditions. This is just a normal condition at the far end of the tank, and then here this is this condition in the middle, because lambda only holds here. And if you do some Taylor expansions, it actually turns out to be this. So unfortunately, lambda is not kind of a normal Dirichlet condition in the sense that it's 0 or constant a. No, it's actually the other variables, which are a function of time. Yeah, so I walked you through this, and the buoy shape here is simply a line, so it's a linear function of y with some angle, which is here, and some keel depth hk, and here's the rest depth, which follows from the buoy shape. So now I use the space continuous Galerkin method. So I use for the unknowns the fields. I use continuous Galerkin second order, just 10 functions, and of course the discretization needs to be consistent. I get again 6 equations, 5 unknowns, and they need to be consistent. So there's a bit of indexing of the nodes. There are nodes everywhere in the domain. There are nodes only at the buoy, under the buoy, so they need to be matching. And at NP I make a mesh so that exactly there is a node here at the waterline. Because it's going to be hairy when it's nonlinear. Then under the buoy you can also have the notation that is all points, all the nodes except the ones on the waterline, and in this case there's only one waterline node which I indicate with NP, and they all have slightly as without anything, with the tilde, with the head, then it excludes the waterline point, and B tilde is the waterline. Of course, this is one point, but if you introduce the lateral direction, it's actually a set of points. Then we use simple test functions. They're Neumann conditions at the end, if you wish. So those are not unknowns. So this is an unknown, and this is an unknown, and they're C naught. The derivatives are not. And then we use, using the Einstein convention, simply the expansion of the fields in terms of these of a summation of these test functions, and a coefficient which still depends on time. And the same for eta. But the test functions are, and the basis functions are Galerkin, so they're all the same. I suppose I shouldn't have had a tilde here. I'm not sure why I had a tilde here. The tilde shouldn't be there. Now we use a trick, and we extend. So lambda is defined under the buoy, but what we do is we extended one element, one width, say delta y, to the left. And that's a trick, and that shouldn't be the case, but that's the trick, and that's the only way to get the discrete equations consistent at the moment. So these are the discrete equations in space. These are the finite element matrices, and here somewhere, here's a vector. But the point is, again, that you have 1, 2, 3, 4, 5, 6 equations, and either you solve the first 5 or you solve the last 5. But if you take the time derivative of this equation, you get another equation, discrete equation. If you take the time derivative of that, that should be this discretization of the equation for lambda, just like in the continuous case. Otherwise, your discretization is not right. And so the only way to make it right, so defining the matrices, but these are standard finite element matrices. So in words, you take the time derivative of the discrete primary constraint, you get a discrete secondary constraint, you take the time derivative of the secondary constraint, and that gives you a discrete integral elliptic equation for lambda, but that needs to be the same equation as if you didn't derive it via this route, but took a discretization of lambda. And we only could do that with the trick that we secretly, for one element, extended to the left of the waterline point, where strictly speaking lambda is not defined. So in time, we simply use constrained symplectic Euler, which is a first order method. So I work it out here for the case where space is continuous, because it was easier to write down. But basically you have a Euler forward step for phi tilde and w tilde, and then a backward Euler or Euler backward step for z tilde and eta, where you use the updates of w in the future time n+1 and the update of phi in the future time to get actually, basically this is what Newton did to integrate its planets, right? So it's the simplest forward Euler case. And you can show that if you take that you want this to be 0 in time, and now I can substitute eta n+1 and z tilde n+1 from these equations, and then I can show that I need to take the time levels for lambda this way, and then I'm again fully consistent. Same trick. So now I'll show some preliminary results. We looked at it so in principle we expect order delta t of the time integrator, because it's a symplectic Euler integrator, and we don't quite find that. By refining delta x, just to be sure that that's not the bottleneck, we get up to delta t to the power 3/4. We can't get it to delta t. So there is somehow, potentially due to this trick, suboptimal convergence. So this is the convergence in space. So what we show here is the energy, and then in blue the results for delta t, and in red the results for half delta t, and the reduction here is square root of delta t, and the reduction here for finer mesh, so for dish mesh, is delta t to the power 3/4, while you expect, if it's order delta t, that it goes down by half. So this is a symplectic method, so you don't find exact energy conservation, there are bounded oscillations, but the bound goes down when you when you decrease your time step, and it should go down by a half if you go to a time step dt over 2, and it doesn't quite do that. Now the spatial convergence is, you expect 2 because it's just standard continuously looking finite elements, and the order is 1.77, so it's not quite the order 2 in different norms. Actually, we did another one just recently, and they all uniformly get to close to 1.77 for once you halve the mesh size. So for all the norms, for the L1 norm, the L2 norm, and the L infinity norm. Now what's nice about this method is that the energy which belongs to the water and the energy part, the energy splits between the water part, the buoy part, and the electromagnetic part, and the transfers this way are consistent. That's the strength of the method. Now we have, this is very preliminary, we have done some try to see when you get the biggest energy harvest. So what's here is the power generated and the power in the system. So it's either power lost, that's in red, due to dissipative features, and this is as function of the load. So here you have one LED pair, 2 LED, basically that scales in a linear case with these parameters, and you see that the power generated goes up linearly, which is what you expect in this case, easy to find, but that the power lost asymptotes out. And you can also plot the power generated, so that's what you want, the wave energy then generated, and lost is due to heat in the electrical circuit. And that it's plotted here as function of the number of coils, and you can argue that the one coil works best. Here the power is plotted as function of mass. Now you would say, well, take infinite mass, but the point is the buoy needs to fit in the contraction, so there is, and shouldn't hit the bottom, so there is a finite size and finite mass, otherwise it sinks off, because otherwise it doesn't float anymore, which is just a sunken thing, and then it doesn't do anything. And you can look at the power generated and lost as function of the incoming waves, and then you see that there is a resonant peak. So there is an optimal wave frequency, and in principle, given C's of different frequencies, omega, there will be a combination. You try to optimize these parameters such that you can harvest most of the energy. But our optimization is still in its infancy. So that brings me to the conclusions. Well, we derived a full nonlinear wave-to-wire mathematical model from variational principle. We made a space-time compatible discretization for the linearized model. It's still suboptimal, there's something to sort out, but at least it's working. I talked with Ralph, we have some ideas, well, I think there are some ideas to see what might work. For wave problems, I prefer second-order methods or even third-order methods in time. But in this case, it needs to be constrained. So it's a classic constrained Sturmer-Fillet method will work. And I don't know, but you can fill me in on that, whether there is actually a third-order constraint, kind of a third-order rattle scheme. But we have a third-order scheme for the unconstrained case, so it would be of interest to figure out what a constrained third-order scheme would be. But that would require, so the second-order Sturmer-Fillet scheme requires 2 solves of the elliptic equation. And the third-order scheme, we expect 3 solves. So the question is, once you go to a higher order, whether you actually gain enough in terms of computational speed. I expect going to second order will gain a lot, and then going to third order, because the amount of steps you need for 6 actually, in this case you need 3, and in case of the symplectic Euler you need 2, you get more overhead. And then, we ultimately want to go to the nonlinear model, and this is just a snapshot of the 3D buoy in the contraction. So, am I there? Yeah, that finishes it. This was some stuff Ralph and I wrote up on the board last week.
Thank you very much for a very nice talk. And now we have time for questions. Or answers.
This extra little element you need, for lambda, is that because you've got a differential constraint that, or what's the? I've seen that before where there's been first order differential constraints have to be met, but it went past very quickly, so I don't really know.
So I don't like it. Let's put that way. That's clear. So in principle you don't want this because your unknown is not defined here, right? Because lambda is defined only to the right here. But when we looked at that system, we couldn't find consistency, namely that if you take the first 5 are equivalent to the last 5, which is a property. And only when I did this extension, it worked out. So it's a trick. I mean, I don't even know how I found it. I somehow found it when I was looking at where, because there was a leak in the normal approach, and then I was just looking, and I knew I had to look at the matrix around here because that's where I expect the problem, and I found that I could fix the leak with this trick, which I don't like. So the people last week, Franco et al., they suggested, well, maybe you want here a DG method, because in some sense you could also reformulate it that lambda is 0 here, but not here. So if you squeeze this element, you kind of get a jump condition. So maybe you can do it like that. But then the whole methodology becomes more complicated, and that's okay for the 1D case. But for in the 3D case and in the nonlinear case, that wasn't going to make me happy. Now, maybe one has to do that, but I used KISS, as Franco said, keep it simple, stupid, right, at first, and then when I need to, I make it more complicated. So maybe I need to make it more complicated.
But you need some kind of interface condition because
yeah.
Because actually there's a jump in your equations more.
Yeah. But when you but it does converge. So, but of course then this becomes final, right? So there is convergence, but it's not the one I expect.
So with symplectic Euler, you can enforce the constraint. You have a constraint. This eta is equal to z.
Yes.
And if you use symplectic Euler, this constraint can be enforced directly.
Yeah. Yeah. So before doing so, this is the case where I only discretize time with symplectic Euler. But then a priori, so symplectic Euler is straightforward, right? You know what to do, right? The colored steps are you know what to do. But the question is, how do you evaluate this lambda tilde? So a priori, I always put a star there, and I don't know what to do. But I know that the top equation needs to be right, and then I ultimately derive an equation.
Your Lagrange multiplier.
Yeah, and then I derive equation, and I know the time levels where I want to take that, and then it's consistent.
But this constraint is linear, is it?
Well, yeah.
I mean, eta and z are both.
Yeah, because they're linear, right?
In the problem.
Yeah, but it's linear because this is a linear problem. In the nonlinear problem, it's nonlinear. But here, because I linearized first to see through the problem, it's linear. But they're unknowns, right? Both are unknowns.
But do you think that the order reduction in time could have to do with this constraint, or you don't?
I don't know. I think it's to do with this interface condition. That's my hunch. That's my hunch. But Ralph thought, well, it may be due to the fact that you couple, and he was suggesting strip set from being an unknown and impose it as a given function. So then basically rather than having this buoy moving freely, you force the motion, and that means that set of t is a given function, just to check whether it being an unknown causes the problem. Rather, and when it's known, basically the W equation goes, and wherever you have set, you put your known function in. Then you could see whether the coupling causes a problem. So that was a good idea. I don't think it will solve it, but he's listening maybe. But time will find out whether that's the case or not.
Sorry, how did you compute the error? Do you have like a reference solution, like a very fine? How did you compute the error?
Oh, but so in time it's just you look at the reduction of the energy oscillation, so that's easy. And in space with Atkins or the Richardson solution, where you use 3 to we use 3.
I'm going to say if you have a fine solution, then you can maybe look at the local error.
But we looked for an exact reduction. It was very, very tedious. I have one, but it's for steady case. It's actually, I have one, but it's for a steady case, and then the flow in and out of the domain. So we could use that, but it requires a slight adaptation. So we use just 3 meshes to do that. So the Richardson or Atkins, in case you don't have an exact solution.
Otherwise, if you have a really fine solution, at least you can see how the effect of your trick, the local error.
Yeah, so another thing, but we didn't do that yet, is to do mesh refinement here, see if that helps, right? Because we now did just regular mesh in 1D, and actually 2D horizontal, we have not an unstructured grid, but you could, but we kind of have an irregular structured grid. But another approach is to use mesh refinement here. What may or may not be, if people know about that, I actually like the inequality constraints, because in some sense I want to get rid of the fact that I have to follow the waterline exactly. In 1D that's fine because in linear case it's fine because it's fixed, but in a nonlinear case it moves. So I would like to take care that you do not have to follow with the mesh where the waterline is. And an inequality constraint can do that, but we have looked in a little bit, but that requires different types of integrators. But they are used in impact problems. You're smiling. But so I think that might be a direction to explore. Because that would make that part of the problem easy. In the linear case it's fine because the domains are not moving, but in a nonlinear case the waterline is moving, and that becomes a pain, right? Your buoy is moving, your waterline is moving, the water surface is moving. So that's much harder.
Okay, thank you very much.